So in the last video, we discussed what the Hell-Volhard-Zelinsky reaction is. It's a way to put a bromine on the alpha carbon of a carboxylic acid, and also what its significance is. Once you have a bromine on that alpha position of a carboxylic acid, you can do an SN2 reaction with ammonia and get an amino acid. So it's a way to create amino acids. We talked about what each of these elements in this recipe does in the previous video, and so here in this video we're just going to think about this reaction from the perspective of synthesis. So you have the carbonyl carbon, right next to it you have the alpha carbon, and when you first treat this with molecular bromine and phosphorus tribromide, remember PBr3 replaces the OH with a bromine. That allows you to have the keto-enol tautomerism. Once you have the enol, the alpha carbon can attack as a nucleophile the bromine. That gives you the alpha bromination. And then at this final step, you hydrolyze the acid bromide and get the carboxylic acid back. So overall, when you see that recipe, what you want to be able to do is say, okay, I know I'll be adding a bromine on the alpha position. And that's it. That's the whole synthesis step. If you see this carboxylic acid and you see, okay, a bromine and phosphorus tribromide followed by water, that's the Hell-Volhard-Zelinsky reaction. That means I'm going to be adding a bromine on that alpha carbon. After the first step, so maybe I'll even draw it out. After the first step, you would have the PBr3 replaces the OH in the carboxylic acid with a bromine. And this Br2, this undergoes keto-enol tautomerism. The bromine is an electrophile that the enol attacks, and so you get the bromine on that alpha position. That's the first step. With the second step, when you add water, you just do a nucleophilic acyl substitution reaction that recreates the carboxylic acid. And so that is that product. This right here. You really just add a bromine on the alpha carbon. So that's the carbon right next to the carbonyl carbon. That's the Hell-Volhard-Zelinsky reaction. Now, if you're just trying to memorize it, it really doesn't help you a lot either in life or in general in this class. So I really encourage you to go back and look at the explanation for all of this in the previous video. But there it is. Once you know the explanation, you can quickly think about the synthesis, putting a bromine on that alpha carbon. Now, that's being given the reactants. You can see how that can be incorporated in larger multi-step syntheses in this next exercise, exercise 2212. So they're asking, how would you make these following transformations happen? There are a couple ways you can make A happen. When you look at this, you might notice, well, I have a new carbon-to-carbon bond that forms. Like this benzylic carbon is bonded to a carbonyl there. There are two ways that you can make that happen. The first thing is, new carbon-to-carbon bond and a bromine sounds like Grignard reagent to me. I'll dump some solid magnesium in there, That will give me my Grignard reagent on that benzylic position. So that will be a nucleophile. Once we have that nucleophile, how can I add a carbon? What electrophile can I add, have it attack? That is a carbon and two oxygens. Carbon dioxide. The carbon there is really slightly positive. It's losing electron density to both of the oxygens. This can swoop in, attack that. One of the pi bonds will break. We'll have added another carbon that has a carbonyl and an oxygen with a negative charge on it. And then you just stabilize that charge with some hydronium, so you do a proton transfer. And now we have a carboxylic acid with the correct number of carbons, the 2 carbons in the chain. Well, that's not all we need. We need a bromine, but notice that the bromine is attached to the alpha position. And so we could use the Hell-Volhard-Zelinsky reaction to put the bromine on the alpha carbon next to a carboxylic acid. So first Br2 mixed with PBr3, and second a water wash. And that would give you your product. So one possible scenario is this one right here. I'll write the sort of steps down. First, solid magnesium. Second, carbon dioxide. Third, H3O+. And fourth, the Hell-Volhard-Zelinsky reaction, so Br2 with PBr3, followed by some H2O. And the hints, the sort of concepts behind this one, because it doesn't help you just to memorize a specific transformation. The concepts behind this are, you saw a new carbon-to-carbon bond, it was a single bond, and you had the bromine, but those two things together suggested a Grignard reagent. You only wanted to add 1 carbon, you needed to make it an electrophile, the reaction we talked about that has 1 carbon as a great electrophile that sort of creates a carboxylic acid is carbon dioxide. You stabilize the positive charge with a proton transfer, and then you'd want to notice that you'd want to add a bromine on the alpha carbon of a carboxylic acid. And that is the recipe, that is the signature, the sort of bat signal for the HVZ reaction, the Hell-Volhard-Zelinsky reaction. So that's one possibility. But these synthesis problems are so fun because they almost always have more than one way that they can get done. So another way that you could look at this and analyze it and think through it is, bromine, instead of a part of a Grignard reagent, I could use that bromine as a leaving group. And I could bring a carbon in, not as an electrophile, but as a nucleophile that kicks the bromine off. In other words, I could use a cyanide. So if I had something like sodium cyanide, remember what that looks like is sodium gives its electrons away, the carbon is triple bonded to the nitrogen, has a full negative charge. So that can swoop in, attack this carbon, kick the leaving group off, and what you'd have after that step is an extra carbon and a functional group. And remember, this is a carboxylic acid derivative. All you have to do is treat that with some hydronium ion, some acid, and it hydrolyzes and gives you a carboxylic acid. So that is even fewer steps than the Grignard reagent. Once you have the carboxylic acid, you look for the other difference. It's the bromine on the alpha carbon. You say, bromine on an alpha carbon of carboxylic acid, easy. That's the Hell-Volhard-Zelinsky reaction. So I use the PBr3 to replace the OH with a bromine. Then molecular bromine adds the bromine onto the alpha position. And you follow it up with some water. So another possible correct answer for this would be first, sodium cyanide, second, hydronium, and then the rest is the Hell-Volhard-Zelinsky reaction. First, bromine and phosphorus tribromide, and then in a separate step, water. So the two possible answers for this that I'm showing in this video are these two. There may be even more. Part of the beautiful thing about these synthesis reactions is how much of an opportunity for creativity you have. How much of an opportunity you have to shine, to be a human being, not just a robot following a sequence of steps, but to imagine your own syntheses, to assess the pros and cons of them, and to apply these new molecules and think about their use in different scenarios. So that's A. Let's think through B. So if you look at B, again, there are a couple ways you can analyze this. Let's first think about it in a sort of retrosynthetic way. Starting with the products, what do we notice? And we sort of work our way back. So what you'll notice is you have a carboxylic acid with a bromine on the alpha position. So you may look at that and say that is a signature for, the Hell-Volhard-Zelinsky reaction. If I just had the carboxylic acid, everything else exactly the same, then I could treat it with molecular bromine and phosphorus tribromide, followed in a separate step by water, and that would put this bromine on the alpha carbon of a carboxylic acid. So then you might look at the original molecule, compare it with this molecule that we would want. And what you'll notice is the only difference is the number of bonds to oxygen. You have 1 in the starting material, you have 3 in the products. So that's a shouting sign that you need to do an oxidation. How do you oxidize a primary alcohol to a carboxylic acid? That's a strong oxidizing agent, something like sodium dichromate and water and sulfuric acid. So really just 3 steps here. The first thing you'd want to do is to turn that alcohol, primary alcohol, into a carboxylic acid by using a strong oxidizing agent like sodium dichromate in water and sulfuric acid. Follow that up with the Hell-Volhard-Zelinsky reaction to put the bromine on the alpha position. So first molecular bromine, followed by phosphorus tribromide, and then shake it all out with a water wash. That does the nucleophilic acyl substitution to get your carboxylic acid back. And remember, this is the end of the exercise, but it's not the end of this molecule. This molecule can go on to live so many adventures. What else can you do with this? You can treat it with excess ammonia, replace the bromine with an NH2, and now you have a strange amino acid. And you can do all sorts of experiments with that. Put it into different living systems, try to make different synthetic meats with it or synthetic proteins, see how those behave. The world is your oyster. All right, last one for this Hell-Volhard-Zelinsky reaction. And one thing that might be a little unfamiliar here, but it's good that you're seeing it, is this abbreviation for a carboxylic acid. COOH is just another way of saying C double bonded to O, single bonded to OH. So these are the same things. So if you ever see COOH, it's a carboxylic acid. And once you know that abbreviation, you can sort of see it very much like in the previous exercise. We see a bromine on the alpha carbon. The alpha carbon is the carbon next to the carbonyl carbon. This is the carbonyl carbon. So the alpha carbon is here. We have a bromine there. How do you put a bromine on the carbon alpha to a carboxylic acid? The Hell-Volhard-Zelinsky reaction, the HVZ reaction. So molecular bromine, phosphorus tribromide, followed by a water wash. And that would turn just a regular carboxylic acid into an alpha-bromo carboxylic acid. Okay, well, how do we turn this original molecule into that? We can see how it really does resemble it. We have a nitrile here. That carbon is triple bonded to the nitrogen. Well, that's a carboxylic acid derivative. All we have to do is a hydrolysis, and it turns it into the carboxylic acid. So here, there are very few steps. First, you hydrolyze the nitrile to turn it into a carboxylic acid. Once you have the carboxylic acid, you can do the Hell-Volhard-Zelinsky reaction to add a bromine on the alpha position. So those first 2 steps put a bromine on the alpha position, but you have a bromohalide, or you have an acyl bromide after that, and you do a water wash to do a nucleophilic acyl substitution and get the carboxylic acid back after that. So if that explanation I'm giving, those references I'm talking about, sound like Chinese or different language, go back and watch the previous video I made on understanding the mechanism and the significance of the Hell-Volhard-Zelinsky reaction. You'll see what each of those different pieces does and how it changes the molecule, how it creates the transformation that you see in these synthesis exercises. So you can see how when you do these syntheses reactions, it connects to everything you already know. All the reactions you already learned from making carboxylic acids from different derivatives can connect now with a further step. Once you have the carboxylic acid, of putting a bromine on that alpha position. And once you have that, you can do an SN2 reaction with ammonia, get an amino acid, and the world is your oyster.